All right, so this week we're going to start moving our way down the system in the depositional settings, and we're talking about siliciclastic environments still. Today we're going to spend some time talking about fans, and we'll talk a little bit about both two different kinds of fans, both alluvial as well as debris flow fans, and how we can think about the processes that occur on those surfaces and how those might get deposited into a rock record. Okay, this image here on the cover slide is one of my favorite places on Earth. It's where I did my master's thesis. This is Death Valley, California. You can see the white area at the bottom is Badwater Basin, and you're looking out from the Dante's View, I believe it's called, here at the, sorry, it's been a while since I've been out there. Dante's View here, and right below the image here would be Badwater, the lowest point in the continental United States. And you're looking out on the Panamint Range at this big, broad, coalesced set of alluvial fans here coming in off the Panamint Range. It's a really cool spot. There's these small alluvial fans over on this side, and then the big, broad alluvial fans coming out that have all kind of merged together on the other side. Those are called bajadas. We'll talk about that throughout the course of this lecture. So we're going to first talk about alluvial fans. Alluvial, the term comes from the Latin to wash against, as opposed to fluvial, which is flow. Alluvial fans typically they're not always, but generally considered to be sort of more ephemeral, or they occur in drier, more arid climates. They're close to the source of water and sediment supply, so they're relatively flashy, ephemeral systems where a river or a channel that's constricted, say in a canyon here, enters into a wider valley and is able to expand outward and create that fan-like shape. Okay, and so just a schematic of how that looks here. You'd have, say, this is in this case it's maybe a normal fault-bounded valley, like a Horst Graben system here, and in this case you have a little box canyon or something like that that's feeding water and sediment out, and as it crosses that scarp, you get to the apex, it's called, or the uppermost point of the alluvial fan, and then the flow becomes unrestricted, and so it can spread out across the valley until and as it spreads out, the flow and sediment disperses, and therefore the ability of the flow to transport sediment, because it's getting thinner as you're going further out, because you're maintaining multiple channels now, and it's branching more, can't carry as much sediment, so it deposits that sediment that builds up the slope steep at the uppermost part and then gradually shallows as it goes out further. You also get fining of sediment as you go from the upstream to the downstream, as you no longer have the capacity to carry coarse gravel or cobbles, and then you reach a point where you have like a gravel sand transition and so on. That's relatively common in alluvial fans as well. Okay. So here's several images over the coming slides of what these look like in nature. They can be quite striking in beautiful landscapes. This is one from northern Death Valley. I'll have a lot of pictures of these from Death Valley because that's where I've spent a lot of time. And again, you can see here's a relatively steep, relatively incised drainage network here. It may be not a very large drainage basin that's feeding this particular fan, and you reach the apex at this location here where the canyon leaves the mountain range, right, and then it fans out across the valley. You can see a very sharp transition here. That might be that gravel sand transition, or an approximation of that, where the fan sort of overall fan shaped deposition kind of changes its character and starts to become a more integrated drainage network. You can see some of these channels are now starting to coalesce again into a larger stream network down here at the end of this fan. Okay. There's some other really cool features that you might notice here is that some parts of the fan may actually be incised. That may be due to tectonic changes, or it may be due to changes in climate, sediment supply, etc. Those can also occur from what we call autogenic changes, or internally driven changes, where sometimes the fans just sort of pulse, where they steepen and then they incise, and then they steepen and then they incise, and steepen and incise. And you can see this in experiments as well as in natural systems. So oftentimes, though, if you're ever in regions like this and you're looking at, interested in looking at stratigraphy, those are the places to go to see some of the inner stratigraphy of active fans, because you can often see a very sharp erosional or incisional face here that you can look at the stratigraphy in of the fan as it's being incised. So that's kind of a cool feature. Here's another great example of an alluvial fan. Again, a very small drainage network here feeding this very small fan. Again, this is southern Death Valley. These are the Black Mountains here. I believe the previous one were the Funeral Mountains in Death Valley. All very happy names. And this is pretty close actually to that first photograph that I showed in the cover slide of this talk. Again, you can see the fan apex. In this case, it's a relatively uniform fan surface. There's not a lot of incision of the old fan, although there might be some shown here. And as this valley is filled in over time, this is occurring at there's a normal fault bounded range here. So as this side of the valley is dropping down, you're building these fans as the mountain range is uplifting and the valley is dropping. You're building fans out on top of each other. You're filling in that basin. And on this side, you end up with just very small fans as you're constantly dropping that, or sort of dropping the fans down below the canyon, essentially. And so it's sort of, if you were to look at the stratigraphy at depth here, you would have, in this case, it's actually thousands of feet of thickness of alluvial fan deposits that are just these small isolated alluvial fans that have sort of just evolved as the basin floor has dropped out and dropped out. This is actually a really cool area. So this is one of the highest relief locations in the United States as well. It may be the highest relief location in the continental United States, where this valley is continually faulting. Here's another image of that. I believe that's the same fan, or it may just be the next one up. Again, from that similar location as the first slide image, you can see that road going around this fan here. You can see the sort of scale of the relief in this case, that of the drainage basin that's feeding this fan. It's a very small drainage basin. In fact, this is a different drainage basin. This is the catchment area for that particular alluvial fan. It's tiny relative to what you think of a normal drainage basin. And so because of that, it's only ever active when it is getting rain right now at this particular moment, basically. And so the flow and the sediment transport of that particular fan is quite ephemeral, quite flashy, right? Now, these are relatively small examples of those of alluvial fans, but they can be much, much larger features as well. Here is a rather large alluvial fan. These are, individual mountain ranges here. I believe this is in the, I can't remember, this might be the Zagros Mountains. And again, you can see one of the features of these alluvial fans is there are multiple active channels often, right? So the channel that may be, when a rain event or a flood event occurs, you may have flow that is distributing over many channels across the alluvial fan top at any given time. And that's relatively characteristic of alluvial fans as well. So oftentimes you will get channels that switch around and move around, but you'll also have multiples that are operating at the same time. You'll get avulsions, but you'll have multiple threaded channels, oftentimes distributing flow and sediment across that fan. There may be locations of the fan that are preferred at any given time, but generally speaking, it's somewhat distributed across. Okay. I can't say for certain, but I think the scale of this is on the order of hundreds of kilometers, whereas the scale of this is less than a kilometer here. You can see the width of that. That's a 2-lane road there. I've driven that road many hundreds of times. Here's another great image of this alluvial fan, of an alluvial fan from LiDAR imagery. This, I believe, is in Washington, but I'm not 100% sure now that I see it. You can see, again, the same kind of features. You can see the channel. This is probably the active channel right here. It's a little bit more incised, but maybe it's more recently been active, say, in this location here, and maybe here as well. Looks like, yeah, the two channels along the margins are pretty active and incised. So you can also see another feature that's often pretty common if you were to go and look at some of these alluvial fans is that, it doesn't necessarily just fill in sediment after it leaves the after it leaves the canyon, right? You can see in this case that there's alluvial stratigraphy or sediment being deposited in the valley floor inside this steep canyon as well. So you can actually get some amount of sediment that gets deposited and sort of just as the fan steepens and drops, or steepens and incises, it would either fill or excavate out those canyons. Okay, so there's, even on such a small scale, there's the possibility for what we would call storage and release of sediment based on just sort of the internal dynamics, the sort of I hesitate to use the term random. It's not quite random, but it's an internal dynamical process that occurs in natural systems. We won't go into too much detail on that here, but sort of a cyclicity that can occur or can arise within the system itself. Okay. And so, as I mentioned at the beginning, that one of the things that occurs as the fan, as you move down system, or as the fan opens up into the valley, is you get what's called flow expansion on the fan surface. So as the flow becomes less restricted as it leaves the canyon, it can widen. It widens not just by actually widening the channel, as you can see right here, but it widens also by splitting into multiple channels, right? And so you can see that the flow here, that's all the flow that fed this channel, or this alluvial fan, came from right here. But as you can see, the active channel is significantly wider down here, and if you were to add up all of the little channels as it expanded out further, it would be even more wide, but the amount of discharge doesn't change. And so in that situation, the shear stress goes down. That is the stress that's available to move the sediment, if you recall, right? Shear stress in an open channel can be approximated by this equation here, where it's the density of water times gravity times the depth slope product, right? So if you think about it, it's the slope of the river times the depth of the river that tells you how much capacity that river has to move sediment, in effect. And if you reduce the depth, but you can see that the slope isn't changing much. If anything, it's also decreasing because of the sediment coming out of suspension or out of transport. The shear stress available to transport sediment goes down. Okay, and so what that results in is, as that stress that is available for transport decreases, the there's a rapid deposition of sediment, right? So the lower the shear stress, the less sediment the fan or the river system can carry, or the channel can carry. And so as you immediately exit that canyon mouth, you start dumping sediment really quickly, okay? And so you end up with relatively steep slopes in the very proximal parts of the canyon here because of that, right? So you can see in this diagram, this is the depth and slope of a river system, for example. And like typical rivers kind of fall into this region here, where you have relatively low slopes on the order of less than half a degree here, and relatively deep depths on the order of meters or so, right? So these are your typical river systems. Subcritical flow falls into this sort of regime here. But then in an alluvial fan, you end up with slopes on the order of 2 to 3 degrees. We mentioned it a little bit today in our discussion session about glacial fans and deltas as well. And so this is kind of that regime that they fall into. And in general, that results in supercritical flow, right? So Froude supercritical conditions are pretty much common or typical on these alluvial fan conditions, right? So you have steep situations where a lot of sediment is coming out very quickly, is no longer being able to transport as the flow expands and the depth decreases. It steepens, but then it quickly, the slope can quickly lower as well from 3 degrees down to 1 degree as you get towards the basin, right? And as you can imagine, that also has grain size considerations associated with it, right? So as you lower the depth and decrease that shear stress, the larger grains are going to become less transportable first, and therefore they will stop being mobile and will be deposited first, right? So here's an image from a very upstream portion of another fan in Death Valley, and you can kind of see, it's a little bit hard to get a sense for what's vertical in this particular location, but you can still kind of convince yourself that you're seeing a slope to this fan, right? And generally speaking, in a river system, you cannot see the slope of the fan or of a river surface because it's such a small scale. But you can see that in this case, there's still a bit of a slope. You could see it probably in some of the earlier broader scale images as well. But you can also see one thing here that will be important when we start thinking about the facies from these alluvial fans versus, especially when you start thinking about alluvial versus debris flow fans, is the sediment here is relatively sorted, right? You can see that this deposit here, which, if I were looking at this, I would probably interpret that as maybe a channel levee at one point, is a little bit coarser than this surface here, which might have been an overwash or a sheet flow kind of feature here. And you can see that there's some errant large clasts, but they're not super common, and it's not just a dramatically mixed grain size in any given location, that there is some sorting that is going on here. And that's a key indicator of being fluvial versus debris flow dominated in many of these systems. So as these fans grow in sort of both the downstream and the lateral extent, they can start to coalesce, and you get these really cool features. And oftentimes this is a function of, it is a function of the sort of combined or the competing influence of the tectonic, uplift versus base level fall of the basin that you're depositing the fan into, as well as the sediment supply rate, right? So they can coalesce into these large, broad features, which are called bajadas. And here's a great example again from Death Valley. This is the Panamint Range here. The image here is, let's see here. So Badwater is down here. The early image, that overview photo, was taken from right about here, actually, looking out across this feature. So if you're flipping back and forth through the slides, that's kind of will orient yourself here. So this was Dante's view up here. Badwater is here. That fan that we were looking at before up close is this little guy right here. If you've ever been to Badwater, if you've ever been to Death Valley, the little parking area that you can go walk out onto the salt flats is like right here. Okay, for anyone who's in any way familiar with the area. And so one of the cool things about this location is this is sort of a half graben system. So if you remember from your intro geology classes, you can get Horst graben systems where there's normal faults bounding the mountain range on both sides, or you can get half graben systems where there's a normal fault bounding the mountain range only on one side or bounding the valley only on one side. So in this case, there's a fault along this side. These are the Black Mountains here to the south and the Panamint Mountains to the north here. And the Black Mountains here are, and actually this is, I apologize, I said north and south. This image is rotated, so it's actually north is kind of off in this direction. I apologize for saying that. There's a fault that's dropping down the valley along this front, okay? And so this side is uplifting, but it's not necessarily uplifting and at the same time as the valley below it is dropping down right next to it. So these fans here have had a chance to sort of coalesce as they can prograde further out into the basin, right? Because the floor of the valley isn't dropping out below them here like it is here. So you get these very large, they're beautiful coalesced alluvial fans over here, whereas on this side of the valley you can see you only get these tiny little alluvial fans that barely make it out, a few hundred meters. Like, this one's a huge one compared to anything else on this side, and that's because as the material is being shed into this side of the basin, it's subsiding further, filling in with more sediment, and so the fans can't really prograde all that far out there. They don't have the chance to keep building. So that's kind of a cool feature there. And this is a relatively common geometry in many half graben systems. If you go and look around in any of the basin and range province in California, Nevada, that kind of region, you'll see a lot of systems that look just like this. Okay, so that's a bajada. So we can start to look a little bit at the deposits that you might expect to see, and you can actually kind of start to see it in this image itself. If you kind of tune your eye a little bit onto the imagery, you'll start to see that there's sort of a variation in sort of surface texture, if you will, as you go from the proximal tops of these fans down to the more distal ends of these fans, which can correlate to a change in grain size, right? So if you were to, there are very few roads, but there are roads that go up some of these big fans here, for example, and you have to have a pretty stout vehicle to get up those because they're pretty rough. But if you were to drive up one of these big fans, you would notice that, as you start out, you're in pretty fine grain size. You don't see big boulders, or large cobbles out here at this part of the fan, at the distal part of the fan. But then as you drive further and further up the fan, the grain size on average increases and increases and increases. So you can think about that in the context of how you might start to build a deposit from one of these fans as it's either prograding, right, or as the fan sort of is filling in the basin, or as or as it's aggrading, as it's building upwards, if that makes sense. And so you can start to think about what deposits you might expect to get at any particular location in the fan, and then start to think about how that might vary as the fan grows outwards or grows upwards, what kinds of deposits you might expect to get where, and how they would stack, if that makes sense. So that's kind of what we're going to try and build here. So if you think about the way a fan, the way the flow expands from the canyon out onto the fan, you can start to think about what kinds of faces you would get in any location. So if you start up here in the canyon, right, like I mentioned, that there would be sediment that can get preserved in the mouth of the canyon itself. And that would be relatively coarse, right? It might be massive gravel, cobble, boulder kind of mixture. It'll still be sorted, but you won't necessarily get bed forms deposited in there, right? Because the flow would be super critical, and you don't necessarily get anti-dunes in, grain sizes of 30 to 50 centimeter grain sizes, right? So you would end up with a massive gravel. Massive means that there's no internal structure from bed forms, right? It's just grains. So you don't get cross bedding or anything like that. Okay. Then as you move out into the sort of mid fan, as you leave the canyon and start to expand the flow more, right? You've maybe dropped out some of the really coarse material, and you've ended up in a situation where multiple generations of flow has been able to create bedding. Now you might not necessarily get anything like cross bedding because the grain size is still pretty coarse here, but you may start to see some potential cross bedding associated with bars, although it's not necessarily common. But you'll also see planar bedded coarse material being deposited there. So large planar bed material. Again, if you remember back to our discussion of bed forms, that say upper stage plain bed, our supercritical flow plain bed conditions were very common in coarser material, right? And that dunes or bed forms are less stable in very coarse materials. So you would expect to get plain bedded or planar cross bedded. Planar cross bedded just means that the cross bedding is parallel rather than sort of these trough shaped cross beds. Okay. Then as you get further out into the distal component of the fan, things start to become a little bit more fluvial looking oftentimes, right? You end up in a situation where you look more like your normal braided river deposit, which we'll talk a little bit more about in the next lecture slides, or in the next lecture set. But you end up in a situation where bed forms may be common, and so you might start to see both planar and trough cross bedding. So planar cross bedding is, again, as those parallel sort of planar features. Trough cross beddings are bed form cross beds that have more of a concavity to them, and again, your grain size is getting finer and finer, and eventually you lose that gravel entirely as you get further down the delta front, and you reach a sort of gravel sand transition that might occur here. And typically in these deposits, that transition can actually be relatively sharp, and there's some physical reasoning for that, which I won't go into too much detail in this class, but it has to do with that change in shear stress condition between whether gravel can be transported or not. So that's sort of a general downstream or down fan proximal to distal assemblage of facies. And you can imagine then, if you were to say prograde this fan in some way, right, then you might get these planar cross-bedding deposits on top of the trough cross-bedding deposits with gravel on top of that and massive gravel. That would be a little bit difficult to do, but to get the canyon moved out in front. But you can imagine that these can kind of stack in different ways to sort of build your overall depositional framework, such that it can either prograde or it can retrograde or it can aggrade, and you might get just stacks of these on top of each other and so forth. So you might get it stepping backwards here, right? You might get trough crossbeds on top of these deposits, so more distal on top of more proximal deposits and so on. Okay, and that can then tell you, as you're looking at the stratigraphy, what the progression of that fan might have looked like through time. Okay, so I can give you some images of some of these fan deposits. Here's a couple of, here's a really nice one from, I believe this is from Panamint Valley, which was the next valley over from Death Valley. Again, you can see these very large scale cross-bedding here, so this would sort of be, you know, channel scale crossbeds or larger. And then you can see relatively larger, a coarser grain material on top here, and this is still kind of cobbles. So this is relatively proximal, proximal medial sort of range here for this particular deposit. Again, this is one of those deposits that was, you know, an incised fan where the fan itself, its channel has cut down into its older deposits, so you can go and look at those. That's often the best way you can go see fan stratigraphy. We talked a little bit about the grain size transition. It can be quite stark and is generally associated with a very sharp change in not just the grain size, but in the slope. As you start to lose all of that coarse material, the slope really dramatically decreases, typically speaking. And so here's a plot of that. These are images from the bed of this fan here, and you can see along a transect here, right, that let's see if those locations are, it doesn't look like the locations are labeled on here, but as you go down the fan slope, you have almost entirely cobbles at the upstream end, right? The sand and the fine gravel more or less just gets washed down fan. It doesn't get deposited. And then by selective deposition, you start slowly settling out the coarse materials until there's basically no coarse material left, right? And at a certain point, the capacity of the flow no longer exists to transport that coarse material, and all you're left with is sand. And at that point, you stop dropping sediment out really rapidly, so the slope is no longer really steep, right? And that's when the fan surface starts to lose its steep slope here and becomes a more gentle surface. And you can kind of see that happening right around here in this particular image. I think it's somewhere in this neighborhood here, right? And yeah, so there's the secondary channel there. So that, yeah, so this would be sort of the transition here. And that varies as a function of the sediment supply, the flow, right? If you have more flow relative to sediment, then the water can carry that sediment further down fan, right? If the opposite is true, you have a lot of sediment available and you have less discharged, less water available, then that fan is going to be steeper. More of that coarse sediment will be dropped out up fan, okay? Until ultimately you get to a point down fan where there's basically no gravel left because the rivers just can't carry it. The channel does not have the depth anymore, and the slope has decreased so that you no longer have the stress available to carry any of the coarse sediment. And so what that might look like in a stratigraphic column, and I think these may be the first stratigraphic columns that we have shown in this class, but maybe you've been introduced to them before. A stratigraphic column is a graphical representation of a section of sedimentary deposits or sedimentary rocks, and typically it's taken in the vertical or up section direction. Now, vertical we'll get into that later. So what this is it's a log of the both grain types and the sedimentary structures and the contacts between beds that you might expect to find in any location. And these are sort of generalized stratigraphic columns for each of these locations here. So these would be sort of the idealized stratigraphic sections that you might expect to find if you were at a proximal or a distal part of the fan. One thing that I should note here is it's convention, generally speaking, for stratigraphers, that the width of the stratigraphic column generally represents the grain size. Okay, so you can see that the wider parts of this column are coarser grain size material, and the narrower they get, the finer the grain size material is, if that makes sense, with the exception of when you get into carbonate materials. So I know we haven't talked about stratigraphic sections in detail here, but that's what we're looking at here. So these would be a gravel, sand sort of conglomerate here in this image, and then this might be a sandstone unit here on top. So this is the sort of near the fan apex, right? And as you start moving further downstream, maybe those these sort of upper fan top deposits, you might end up with some finer bedded material as the fan progresses, right? And then this sort of, you end up in these graded deposits here that are possible as you go further down the fan from these coarse to fine. These bars with dots in between them indicate silt or sandy silt sometimes. So the lines indicate mud and the dots indicate sand, and so that symbol generally means silt, whereas this means sand here. So you end up with cross-bedded sands grading up into silts, right? So as the flow recedes or wanes after a storm event or a flood event or something like that, or as the fan back steps a little bit, you would get this what's called a fining sequence here, right? And then as you get further out into the distal portions of the fan, the silts and sands are sort of the norm, but maybe every once in a while you get a large event that comes through and deposits some coarse material further out on the fan, and that's what's represented here, right? You have your silts and your sands out in the distal portion of the fan, but then maybe there was a big rain event or something like that, and you got an influx of coarse material. This kind of a symbol here means that it's a sharp contact, right? That it's a very abrupt transition from the sand to the conglomerate here. Okay, and then as you get further out, you might be in a lacustrine deposit, for example, or something like that. And so every once in a while, maybe you'll have lacustrine sediments, but then every once in a while, maybe you get some sort of a sand bed that comes out as you get a storm event or something like that. Okay. And so that's what those deposits might look like, and you can imagine as that fan migrates either up valley or down valley, depending on the conditions, that these sequences might stack one on top of each other or grade into each other to start building your overall fan stratigraphy. Okay. And I know I've shown this sort of this, I've given you a little bit of this background from a previous slide, but ultimately that sort of those stacks of stratigraphy can end up building out a full valley stratigraphy that can be really useful in thinking about the paleohistory of the valley, whether it be your interest in the tectonic history or the climatic history. So in this case, these yellow boxes might indicate that this is the lake sediments, and then the darker orange color here might indicate the fan deposits. And you can look at the gravel sand transition or the fan to lake transition as a function of depth, if you say had some seismic data or some well log data or something like that, and start to see how those fans prograded into the valley and backstepped away from the valley through time, which might tell you something about the depositional history, whether at some points in time the fan systems were more capable of carrying coarse sediment further out into the valley, and why that might be, and so forth. But this also shows you a little bit more of the structure of the fault system in that valley. Again, this is now the image has been rotated so that north is actually up in this image. Again, to orient yourself, this is bad water, so the normal fault was here, right, which is this system here. So we can move on from alluvial fans now. This would be a good time to take a break if you needed to do that. Sorry, I didn't break this up into two separate lectures. We can move on from alluvial fans now to debris flow fans. And these often have relatively similar shapes or forms, but they have a slightly different, they're different in their genesis and also have some different sedimentary characteristics or depositional characteristics. And these result from what are called debris flows, which are a type of flow that contains so much sediment that the particles are constantly in contact as they're flowing. They're not water suspended particles. They're actually particle suspended particles, and the water is contained as a pore fluid. So it's actually between the grains, but not supporting the grains, if you will. So in an alluvial fan, it's the flow and the shear stress of the fluid that is driving sediment to be transported. In a debris flow, it's actually the momentum of the particles themselves that cause them to collide against each other. And so it's those elastic collisions of particles that basically allow grains to bounce and vibrate and expand that or dilate that whole sediment body, if you will, enough so that particles can start to move past each other and the whole thing can behave like a fluid, right? And there's a lot of details about these that can kind of change their mobility, but as the more fine-grained sediment that's suspended in the water, that can increase the viscosity of the fluid, which has the effect of hindering the movement of fluid around grains. And actually what that does is it sort of basically makes it so that the water can't escape the system or segregate in the sediment, and so it can cause the whole thing to basically move as one single fluid phase of sediment and water all together, and houses and trees and cars and whatever else comes in its path. Okay, one thing that maybe we don't need to go too much into detail on this, but as the whole system is strained by shear, right? So as this debris flow starts to move, the whole framework starts to shear, right? And so you get strain that starts to transfer stresses from the particles to the fluids themselves, which causes the fluids to expand and basically promotes liquefaction. So the more these things move, the more they want to move, is essentially the ultimate outcome of all of that, right? So that once they start going, there's a lot of things that compound to make them more and more and more mobile, sort of almost like a runaway effect, that the particle collisions make the particles more mobile, and the particle collisions and the shearing that gets driven by once the thing starts moving sort of dilates the pore space, and that promotes motion, and that also transfers stresses into the fluid, which promotes motion. So they can all kind of compound to create very mobile deposits. And these debris flow fans can be quite striking. The deposits that are formed by this, they can be very steep, and they can move really, really, really mixed grain size deposits, anywhere from boulders to mud. essentially. And so you can see this is again from the Black Mountains in Death Valley. You can see it's a relatively steep, on the order of 10-degree deposits. They're relatively unchannelized, or they might be very kind of hummocky like, if you will, almost. They can get sort of lobe deposits as individual debris flows create individual lobes here, so you can kind of see the desert varnish on this particular debris flow fan really dramatically gives a sense for the relative ages of these deposits, right? So desert varnish kind of develops as a veneer on the exposed surface of rock in the desert here. It's a photocatalytic kind of effect that allows these metal oxides to form on the surface of the rock. And so the darker they are, generally speaking, the older that they are. So you can see this is a relatively young debris flow with some slightly older ones here and older ones underneath and so forth. So they're multi-generational, very steep. This is barely above the angle, or barely below the angle of repose for dry sediment. Okay. But these can actually, the debris flows, if they're wetter and finer grain, these are relatively coarse grain, not a lot of mud that supports these particular fans, and so they can, they don't make it out too far. But if they get, finer grain material incorporated in there to support that that shearing and that pore pressure development, then they can actually migrate and flow quite a bit further. I think the initial image that I showed at the beginning of this discussion here, I think this was from Montecito, California, where the a debris flow of a hugely mixed grain size range came out and basically buried part of that town quite a ways downslope. Here's another great image of some debris flow fans. Normally I would ask the class where they think this is from, and so maybe I'll leave it there, and we'll talk about it in our next discussion. So think about where this debris flow fan, these debris flow fans are from, and maybe we'll talk about it. There's some clues that might help you in this image, but it's a pretty cool set of imagery. And so these deposits from these debris flow fans, because of the fact that they are not being driven by fluvial flow, but by, granular shear, are relatively unsorted. They're just, there's just going to be a mess of grains when you see one of these things. So it'll be very similar actually in nature to, or in character to the diamictites that we talked about when we talked about glaciers, right? So you can see in this image, here's a debris flow coming out of a canyon. I believe this is in Utah, and you can see there's a big, half meter, 3/4 meter rocks, large cobbles, boulders, and all the way down to mud here in this debris flow fan. Okay, here's another great example. Huge boulders, cobbles, no sorting to speak of, no depositional bedding or anything like that to really write home about. And that's relatively common. There is one kind of sorting phenomenon that can happen in certain types of debris flow deposits, though, where due to the motion of the grains, the coarsest material may end up on the surface or at the front of the deposits. And the reasoning for this, it's sort of if you've ever gotten like a can of mixed nuts that have, the big Brazil nuts all the way down to peanuts, right? And if you bring that home and you open it up, you'll see that the Brazil nuts are always all on top, and there's like 6 of them, and then the rest is like peanuts and cashews, right? And it's the same thing that happens. It's the reason why all of the crumbs in the cereal bag are left at the bottom of the cereal bag, but the Cheerios are at the top or whatever, right? It's through the process of this shearing and motion of the deposit, every time a particle or every time any number of particles moves, it's easy for the finer sediment to sort of fit into the pockets below the coarse sediment, but the coarse sediment, like the boulders can't necessarily fit underneath the finer sediment very easily, and through the combination of thousands and thousands and thousands of motions, the coarse particles end up kind of getting rafted or floated onto the top, essentially. If you ever get a a handful of a really mixed grain size sand with some pebbles and gravel and stuff in it, put that in a jar and kind of just shake it for a while without really railing on it, and just kind of give it some agitation for a while, and you'll see that the coarse material will eventually end up on top, right? And that happens fairly commonly in debris flow deposits as well, and it's a pretty telltale sign actually of a good debris flow, as you see this jumble of boulders on top of the finer grain material underneath. Okay. Here's another kind of image of that on the surface of a debris flow. You can see a relatively mixed grain size setting. This is a mixed debris flow and alluvial fan, so there were both debris flow deposits and alluvial deposits kind of mixed in here. But you can tell that this one, there's not many rivers in this particular part of the world that would carry that size of a boulder, right? Here's an up-close image, and you can see that that is relatively similar to what we talked about with diamictites, and it may actually be relatively difficult to determine the difference between a diamictite and, in fact, between a glacial diamictite and a debris flow deposit, which from a strict definitional term could also be referred to as a diamictite, right? In this case, you have a larger clasts supported by a muddy matrix. These are submarine debris flows in this particular image, so these were debris flows that occurred underwater, but they can occur underwater or subaerially as well. But you can see that, again, these are matrix supported conglomerates. The clasts are not touching each other, they're surrounded by mud, right? And that's relatively indicative of a process like this that is not hydraulically sorting the sediment. Okay. And so just like with fan deposits, we can think about the facies distinctions in a debris flow fan or in a mixed alluvial debris flow fan, and this is a pretty common situation to see in a lot of especially arid environments, is one of these mixed alluvial debris flow fan deposits, and because it's relatively uncommon to have just a purely debris flow fan. It's not impossible, but oftentimes they will have some fluvial component at some point, where you might see deposits. I apologize for the kind of graininess of this image, but where in the proximal region you have a lot of debris flow material, right? Gravity flows, debris flows are often referred to as gravity flows. That includes debris flows and landslides and other types of non-fluid supported flows. But then you might also have river channels that cut down into those debris flow deposits, and in the proximal sense, but then as you transition further down fan, you might end up in a situation where you have fewer of those unsorted debris flow deposits, channels doing their alluvial fan thing. And then as you get out to the sort of outer fan distal region, it's very unlikely that the debris flows or gravity flows make it out that far, and you end up in the channelized or sheet flow deposits in that case. You might see this represented in this way. This is a nice facies diagram for a fan here. In this case, you have more of a debris flow dominated fan versus an alluvial dominated fan. Again, you might have debris flow or rock avalanche deposits still preserved, but in general, up here you'll have sort of more of these poorly mixed, poorly sorted debris flow deposits, versus in the alluvial fan you might have a slightly shallower slope, and B, more bed form deposition. You might still have rock avalanches and debris flows, but you'll get sort of that characteristic fining downstream or downslope, which you don't have, generally speaking, in a debris flow fan, right? Because of the momentum aspect, they generally tend to not fine or get sorted downslope. and so forth. Okay. So just kind of leaving you with a couple of last images. I love some of these images. This is a great example though of sort of a mixed deposit, if you will, right? You can see that there's some sorting going on here. So this is probably, this may have been an alluvial deposit here, and this was probably a debris flow here. You can see a large boulder and a bunch of poorly sorted matrix supported clasts here, and then you have another nice better sorted cobble bed here. You can maybe convince yourself that these clasts are imbricated, right? You can see that they're kind of stacked all in one direction to be in a more hydrodynamically stable configuration. So maybe this was a sheet flow that came out across, or the surface that had previously been laid down with a debris flow. And then another debris flow deposit here, which maybe you could convince yourself has multiple generations, multiple beds of debris flows in here. And then again, now you're at the surface and you can see it's better sorted. So you can start to look at these and say, oh, okay, I think I see, poor sorting, huge clasts mixed in with mud, mixed in with cobbles. This tells me that that's probably a debris flow deposit here. This is better sorted, maybe imbricated, so maybe this is a fluvial or alluvial deposit. Sorry, not a fluvial, alluvial deposit. So it may be a sheet flow type situation, and start to play around with your interpretations based on those kinds of things. Does that hopefully make sense to everybody? And then just before we break for this lecture, there's some just absolutely stunning debris flow fans, debris flow and alluvial fans, and mixed debris flow alluvial fans on Mars in some of these craters. And so here's just a great example. This is just eye candy for this lecture of these are those alluvial fans here filling out into this crater that may at one point or another have had a crater lake in it. And then you can see that there's some other fans that may be more debris flow dominated here, right? So we'll have one more lecture this week that will be on rivers, and again, that one will be maybe a little bit long as well, but that'll wrap up this week, and then we'll move on from there downstream to deltas. So thanks.